all of you then a relaxing lunch break and are ready for the coming talks in our session about characterization of ceramic, polymeric, and metallic materials. My name is Jürgen Stampfl. I'm professor here at TU Wien for materials and additive manufacturing, and I'm chairing this session. And I'm happy to announce our first speakers. I suggest we directly jump into the session to be able to keep to the schedule. So the first short presentation will be given by Veronika Miron from Johannes Kepler University in Linz. And she's going to talk about material characterization of 3D printed silicone elastomers. So again, please also have a look at the YouTube full presentation, but Veronika, she will give a short version here in a couple of minutes, and then we have 5 minutes more or less to discuss her presentation. So please, we are looking forward to your results and presentation.
Thank you.
We cannot hear you yet.
Sorry.
I can see you and your presentation, but I don't hear you actually. You are unmuted somehow, but
maybe now it's working. Does it work?
Yeah, now I can hear you. Yeah.
Okay, great. Sorry about that. Yeah, good afternoon from my side. Thanks for the introduction. I will quickly repeat a bit from the online presentation, but I'm keeping it way shorter than that. I'm presenting about the mechanical characterization of 2 3D printed silicone elastomer types. And this work was funded as part of the project Medical Education in Surgical Aneurysm Clipping, short MEDUSA, which is an Upper Austrian research project to develop hybrid simulators for aneurysm clipping surgery, so to train surgeons to do these kind of operations. And in order to get the best outcome, we needed soft brain lobes, so models of soft brain lobes. And we have all the advantages of additive manufacturing, and we have advantages of silicone elastomers. The ones from additive manufacturing, you probably all know. But silicone elastomers have very well damping properties. They're used for sealing in biomedicine. And usually they're processed by mold making or prototyping also, and for these applications. And now we wanted to combine those advantages. So what we did is we built a silicone 3D printer. We used a commercially available print head, the Viperhead 33 from the company Viscotech, which is allowing us to print with 2 component silicones that are going through a static mixer and then are extruded through a nozzle that we can choose in size. After each layer, so conventional extrusion-based additive manufacturing, after each layer, we go over it with a halogen lamp, which produces a lot of heat. So we have thermal cross-linking of the silicone elastomers. There's actually only one silicone advertised for this purpose. This is the Silastic 3D 3335. And we also wanted to check out if we can print with other kinds of silicones. For example, we have here biocompatible, usually molded silicone elastomer, the Dragon Skin 10, and we use the slowly cross-linking one. There are print parameters, but you can also see the details in our paper. And we printed uniaxial tension, so for tension, compression, for biaxial tension, and for pure shear, we produced the specimens. And for the Dragon Skin material, we printed the cubes also for compression tests. I will only show now the compression test results because those are nicely to be given in an overview. The main thing that we found is that when we have the 100% filled cubes printed with this Silastic, with the Shore A50 silicone. So here we have 100% filled and 10% filled specimen. So we see a lot of difference in the compression behavior. And here in between, in gray, we have silicone elastomer with the Shore A10. So this is the Dragon Skin material. And we can see because we need these very soft grain lobes. We don't have to necessarily go to a very soft silicone elastomer, which is a bit harder to print. We can also just reduce the infill consistently, and then we get a way softer behavior. This seems logical so far. We can also see hysteretic behavior, and we tested at different strain rates, but we couldn't see any significant difference. So this is also nice for our application. Basically, what we would like to show with this paper is that normally you have to select the silicon specifically for your application. So the Shore value has to fit the application, because with molding, you can only produce 100% filled models. But with 3D printing, these silicon elastomers, you can actually produce a foam-like behavior, and you can use this Shore 50A, for example, for Shore hardness values down to 0, 0. So this is very beneficial for us. Thanks.
Yeah, thanks a lot for this interesting insight into a material which is quite interesting for many medical applications, silicones, and they are obviously not so easy to process. So thanks for showing how this can be done. Do we have some questions from the audience here? I'm checking, but there's one from Bettina. At least
so, my question is, how does the cross-linking process of the silicones work? So which functional group take place in the process, and what is the cross-linking agent?
Maybe directly. I'm not a chemist. I'm a polymer engineer, and we try to use commercially available silicone elastomers. So I don't know anything about the chemical process in the background. What we are doing is we put the materials in the printer, and we see the properties that we can achieve with these existing materials. So we are not trying to make new materials. We really try to use existing materials.
Yeah, but this was extruded, right? So do you pre-mix them? They are probably mostly two-component silicones, right?
Yeah, so we start with two separate components. Here is when we only want to have small amounts of material. Here we also have possibility to fill like half a kilogram each component A and B, and through these tubes we transport them. Here, then they come in this continuous piston system. It's a conventional dosing system, and only in this part in the front there is the static mixer where they actually come together, and then they're mixing. And at the end, there is this. We use the 0.4 millimeter nozzle through which it's extruded. It's still liquid. The Elastic, actually, the commercially advertised for this purpose silicone, it's not cross-linking without heat implants at all. That's actually one of the disadvantages of this dragon skin material, that when you leave it in this system, the component B actually starts cross-linking. But we don't, with using existing materials from the market, you don't get the details of the consistency. So the goal would be to get materials that don't have.
And these traditional silicones, they are usually very slow in reactivity. So do you have problems then? Because I guess it will take quite some time until they cure.
No, with the heat, the cross-linking is very much faster than at room temperature. So we achieve temperatures of 70 degrees with this lamp. When we close the system, we can get up to 100 degrees. So we speed up the cross-linking process a lot by this. And the Elastic doesn't cross-link at all at room temperature. So.
Okay, and in terms of, usually you want to make quite small channels in these medical applications. If you use silicone, very popular in biomedical engineering, and in many cases you want to make some very detailed and in many cases small channels or things like that. So can you a little bit comment on the achievable smallest feature resolution you can achieve with such a process?
This is a very good point. Actually, this system is not made for fine details. With this extrusion, and because it's dealing with liquids, I would estimate 0.5 millimeter accuracy. So it's not made for fine details. But when you imagine we have to print whole brains, so we need the mass more than the details. So in order to produce bigger parts, we are dealing with anatomical models, not with implants that have need special, also biocompatibility.
Okay. Yeah, thanks a lot for your presentation once more. I don't see, I'm also checking in the chat, but no one is raising his hand and no comments in the chat. So thanks again for this interesting insight. And we can then directly move to the next presentation, which is given by Tiago de Silva from the University of Porto. He's going to talk about mechanical behavior of maraging steel produced by SLM, so switching from super soft to super hard, I would say. So looking forward to your short presentation.
Thank you for the kind introduction. I hope you can listen and you can see.
Yeah, it's acoustically, you're a little bit hard to understand. Maybe I can try to get a little bit closer to the microphone if possible.
Sure. Is this better?
Yeah, this is a little bit better now, yeah.
Okay. So thank you for the introduction. And together with my colleagues, I'm going to show some of the results and the brief analysis of the mechanical behavior of the maraging steel produced by SLM. This is especially important, this study, to generate comprehensive material data towards numerical simulation of the additively manufactured maraging steel. This is interesting because sometimes we want to simulate very intricate geometries, so we need the accurate mechanical properties, and this is where this is the focus of this study. For that, so distinct specimens were manufactured according to the purpose of each test. There is cylindrical geometries and small square geometries for compression testing in different loading directions. There is specimens for tensile testing, for physical and thermal testing, and also for the more intricate multi-axial compression testing, which I'll be focusing later on. We did the typical checking for the sanity of the material. We were very satisfied with the porosity. It is very, very dense. Chemical composition was also compliant with the standards. The micrographs also show the typical morphology of the AM structures, and also the conventional is very similar to what is found in the literature. The thermal properties, we measure them through we measure thermal expansion coefficient through the electrometric tests, and these tests show that the phase changes occurring in the conventional and additively manufactured are slightly different in intensity, showing the probably also different austenite content. With regards to other thermal properties, such as thermal conductivity and specific heat, we notice that the results seem to be very similar depending on the metallurgical conditions. So there is almost the same values depending on IM or CM. Moving on to the mechanical characterization. So we did compression tests for different strain rate values, quasi-static, so almost no speed, and also 300 per second, 200 per second, and 600 per second. This is slow motion video of 100 per second. This is a high speed compression test. The results from the quasi-static compression test show the typical results that we can see. So the additively manufactured steel presents higher strength, and within the two distinctly directions of the additively manufactured compression, we noticed that one of them has higher strength, which is related to the columnar grain formation. With regards to the very high strain rate tests, for small strains, we note that there is an increase in the mechanical strength of the materials in both additively manufactured and conventional manufactured steels. However, for increasing strain, we notice that there is softening, and this softening can be very intense, especially in the compression, in the conventional material. It goes well beyond or lower than the quasi-static response that we can see here. We also did tensile tests. These were done for different stress triaxialities with different notches. We obtained the fracture strain through simulation, through fitting of the curves and determining plastic and damage response. And with regards to the multi-axial specimens, we designed notch geometries to test different stress states. So with a pressure angle smaller than 90 degrees, we have a mixture of tension and shear. With 90 degrees, it's theoretically pure shear, and larger than 90 degrees, in this case 120, it's compression and shear. So we could characterize in different stress states. We did this for additively manufactured and conventional once more, and because of the higher ductility of the conventional, it did not fracture. So we had to stop the test for the conventional steel. Once again, the fracture strains and the flow stress curve was determined through numerical inverse analysis. Due to the slight differences between the compression curve and the tensile curve, we determined a flow stress through a hybrid approach that was compliant with both tests, as upper and lower boundaries for the hybrid approach. The test also enabled to determine damage law. And here we can see the simulation of the compression multi-axial tests, which is very satisfactory, and also the deformed shape of experimental and numerical results that is also very, very relatable. And with all these tests, we arranged this data that is available to everyone that wants to simulate this material, and we will make available in the following structural procedure publication. So thank you very much. I'm here to answer some questions with the remaining time.
Yeah, thanks for this broad overview of also very challenging material for selective laser melting. And with excellent strength properties if you do everything right. Are there some questions? We still have some time for discussion here. I'm checking. So I've one. So typically, or two actually. Typically, maraging steels they are very beneficial in terms of tensile strength, right? So you made tensile tests, but you didn't give the stress values. You just gave the load values. So how do these does the tensile strength or the yield strength compare to the conventional? Those are simulations, right?
Actually, the green and the black curve are experimental curves.
Ah, okay. Because you also had a slide with the tensile tests, and there you just gave the load. Okay, but here. Yeah, so you have some issues with elongation at break, right?
Exactly. So when you compress the when it's a compression test, you can obtain very large strains. When it's a tensile test, this is not percentage; it's actually the strain. So
yeah, sure, but it's still
100% here.
Yeah, but still, it's about 4% or something like that.
Yes, and I also noticed that the conventional material is much more ductile than the additively manufactured.
Yeah, but I mean that's the critical thing always, yeah. Because if you have such a high strength material, you even are more sensitive to defects in. Did you look at the fracture surfaces in the tensile samples?
Yeah, we did, and we could find some porosity coalescence in the additively manufactured samples, which we attributed to their fragility, to their lack of ductility when compared to the conventionally manufactured. That those images are not in this presentation for simplicity, but of course, if anybody is interested, we can get in touch, and I'll show that I'll show those results as well.
Mm-hmm. Okay, but that was my question. I just check here. I don't see anything. Let's briefly check the chat. No, nothing. Then thanks once more for looking in these very interesting materials with a lot of potential for many applications. So thanks. And we switch over to the next presentation, which is given by Syed Lotfian. Hopefully I pronounced that correctly. And the presentation is entitled Additive Manufacturing of Microarchitecture Composite Metal Joints for Renewable Energy Applications. So we hand over to our presenter. I don't see. Yeah, here we go.
Hello.
We see you, and I also hear you. You can just share your desktop.
You can see me?
Yeah.
Yeah. Okay. I thought it's just I had to send my presentation there and as a video. Just give me a second.
Yeah. But you can also just we need to make it somehow short that we have plenty of time for discussion. So
sorry
you have to somehow pick out 2 or 3 slides from your presentation and then show us the most important things. If you
okay, I will share. I hope you can see my page.
Yeah, I see something. Yeah.
Okay.
Also, it's not in the presentation mode yet, but also that this is not such a big issue. Yeah, now it's here.
It's okay. You can see the full page, yes?
Yeah, right. Now we see the full page.
That's great. Thank you. Okay. Thanks. Hello. My name is Syed Lotfian, and I'm going to talk about the microarchitecture composite metal joints by additive manufacturing for renewable energy application. I am a researcher in materials and structure in Center for Advanced Material for Renewable Energy Generation, so-called CAMREG. It's a EPSRC project at the center in collaboration with the University of Strathclyde. I am already working in with the University of Edinburgh and Strathclyde. The aim is to use the novel, smart, multifunctional materials and structure materials and also the advanced manufacturing technique to address the existing and arising challenges in renewable energy conversion and energy storage. My work is mostly focused on the extending the lifespan. I am also a member of an offshore engineering institute in the university. My main research focus on remanufacturing, additive manufacturing, a smart structure like morphing and adaptable structure, and also dissimilar joining strategies. Conventional processes to bond dissimilar materials, particularly metals and the composites part, resulted in a very poor mechanical performance and durability. the emerging additive manufacturing technologies present attractive prospect to produce the bespoke joint for hybrid structure. The aim in this project is to develop a reliable 3D printed composite metal hybrid joint by additive manufacturing. As you can see here, the sandwich metal parts will be, there will be pins on the sandwich metal part, which produced by LMD, and also the fiber part, the carbon fiber plate will be printed with the 3D printer, the composite 3D printers. During this project, we have different industrial and institutional collaborators from different parts of Europe and inside the
Sorry,
UK.
but we need to speed. Also, somehow, if you present all your slides from the full presentation, then we don't have enough time. So we need.
Oh, okay. Thank you. I will go to the result then. Yeah. Just. I show fastly this part that we managed to 3D printed the composite when the hose is also already there, and they are reinforced during the manufacturing. And then also we run the FEM analysis to address the most efficient hole pattern and check the performance of the hybrid joint. And for the additive manufacturing, we use the hybrid manufacturing platform, which we could, and I'm passing this part, just different strategy, different building strategy. We'll check for the metal parts. The interesting part here, we use a off-axis camera installation, the infrared camera installation from the NIT Europe. And the good things about that is, as you can see, we can have control on our melt pool. And if we can already is on process to have a kind of feedback control system to check the sizing during manufacturing. This is, from the microstructure, we find that during the process, the microstructure of the material is controlling the two thermal factors, the temperature gradients, and also the solidification rate. And we checked the lowest phase, the matrix gamma phase, and also we check with the EBST result in on the substrate, and the interface area, which we have kind of recrystallization, and also we have the columnar grain. Actually, this changing the G and R within the melting pool, we have a different microstructure features, include the equiax near to the interface, and elongated grain here, which with different building strategy, we can see different passes also. The other things we checked up to now is the residual stress on that, and we use the counter method system with the cutting, and then if we put the cut artifacts out, then we have a tensile. We find that we have a tensile residual stress, which is developed near to the top part of the printed parts, and then we have a compressive residual stress developed around the interface. We check that with different laser power, and we find the optimum of that. Already we are because of the COVID, unfortunately, we had many problems with the with the experimental part. But as a whole, I can say that now we have all the things. We are starting to print the pins itself, and then after that we will do the checking the joint and checking and trying to correlate the data from the simulation with the real result that we will have there. And thank you. Sorry for the I was under the impression that it will be the video just going there. Thank you for that.
Thanks for your presentation. Obviously, you didn't listen to the other talks, otherwise you would have known.
Sorry, yeah, that's
anyway. Are there some questions from the audience? Yeah, Jan, please.
I have one question. Can you just quickly repeat how this relates to renewable energy applications? Or?
Okay, that's the using of this this sandwich structure is for submarines, that they are for the weight consideration in some part of that they are using this. Also the joining of the joining of different part of the composites to the metals on the blade. It's between the composite and different metal parts.
So it's a fixture. You're not aiming for any kind of electronic or electric behavior here.
No, no. But okay. we are working on different projects on a kind of let's say self-warning hybrid composite sensors, which it can be implemented in the composite parts.
Right, thank you.
Thanks.
Okay, thanks once more. So it's time to move on to the next presentation, which is quite a different topic, but also related to the characterization of materials in this case. And the presentation will be given by Sonja Baumgartner, who worked in my group, and now she's left the university, but she's going to give her presentation about her work she did recently. And her talk is entitled Digital Materials, the New Dimension of 3D Printing. So Sonja, please go ahead.
Okay, thank you. Okay, you can hear me and you see my screen?
Yeah.
Perfect. Thanks, Jürgen, for the introduction. So, as Jürgen already said, my project I'm presenting today is about digital materials, which is a concept we've been working on for many years now, and where we try to combine different printing strategies in order to selectively modify parts during the printing. And the way we are doing this is by combining SLA and inkjet printing to use the advantages of both systems in one combined hybrid system, which is quite challenging because they have completely different boundary conditions and resolutions and so on. But in former projects, we already showed that it leads to quite promising results, like you probably heard in one of the talks of my colleagues on Wednesday, Johannes Stögerer. He already presented one of those results. So we were able to modify the thermomechanical properties, increase the toughness of structures by selectively placing weak interfaces, for example. But this project I'm presenting here is more or less enhanced, or is an enhanced version of what we did in those former projects. For this, we worked together with Cubicure, where we combined the inkjet with a new hot lithography process of Cubicure. Cubicure has a new large-scale process, which enables quite a few things. I cannot go into detail right now. You will see a lot more in a few months. But so far, I can say that this project is a continuous, this process is continuous, and it has quite a big building platform of 1 meter times 300 millimeters. And we are now able to produce large parts, which can be modified by inkjet printing, and very many parts at once. And it also enables stuff like curing the ink afterwards, which has not been possible in the former versions of the hybrid printing. And what is even more possible is to process, let's say, difficult materials. So high viscous materials and highly filled materials, for example, as you can see on the bottom here on the page, which is an artificial ivory structure, which has been colored. So with this new system, a lot of things are possible, and I'm really looking forward to what can be done in the next months and in the next time. And if you're interested, please watch my talk again. That's it for now.
Okay. Yeah, thanks, Sonia. I will go and check if we have some questions here. None yet. But maybe I can comment a little bit on you introduced the process, but which chances and opportunities do you see on the material side using such processes? So what's the motivation to develop such new processes in terms of material science?
Well, by one of the drawbacks from SLA or from the SLA side was that you cannot really do multi-material printing. Well, on the other hand side, inkjet can do this, but inkjet has its limits because usually the parts are very brittle because the resins has very low viscosity, and by combining those two, we can produce structures which have a good resolution and good surface quality from the SLA, but also with the SLA part, we can print very high viscous materials. So hopefully more tough materials. And by combining it with the inkjet, we can, as I said, selectively place interfaces which have impact on the thermomechanical properties. And as we showed, we could increase the toughness for some combinations, but I think there are even more possibilities like strengthening or selectively modifying the surface of the parts, and yeah, more.
Okay, thanks. There's a question from Florent Hanard.
Yes, interesting talk, thank you. I was wondering, in your presentation, in the first part of the video, you have shown some results on tensile test of, and then you compared the reference sample with 100% inkjet, in which you see some softening. But what's interesting to me is that despite the softening, you have some strain hardening capacity. I mean, it seems that you do not, you are less sensitive to necking, I guess. And I was wondering, like, have you looked at what's happening within the material? Like, what are the micromechanisms that occurs during the deformation, especially at this large strain in the curve?
Yes, actually, we tried to look at it. It was pretty difficult at that time because we weren't able to distinguish between the ink droplets and the matrix materials, as I said. So we tried different microscopes and tried to see where the crack goes and what causes actually the behavior. Actually, since I left the university, my colleagues tried a lot more and used fluorescence dyes and already showed that the drops have significant influence. So you see on the surface, when you break it on the surface, you see definitely that the cracks go or around, or yeah, they are not stopped at the weak interfaces, but you see the surfaces behaves different. So you can really see the toughness in those areas where the ink droplets are. So it has an influence. Yeah. So far in this first study, I was not really able to show or that the micromechanics. We just saw the tensile tests and the strain that can be increased. So the strain rate can be increased and the toughness in the Dunstad test could be increased.
Then maybe just a small complementary question is that you said you cannot differentiate between the droplets and the matrix, but because they have the same color, I guess, but do they have the same density and everything? Could we use, I don't know, maybe thermography or something else?
It's pretty close, yes, because it's in those first studies it was both based on acrylates and methacrylates, so the density was pretty much the same, and it was really hard to distinguish. So actually, not really being able to distinguish between the matrix material and the droplets. But we definitely saw a difference between with and without inkjet.
Okay, thank you.
Okay, thanks, Sonia. I'm just checking the time, so we are perfectly within the schedule. So thanks once more, and also for giving enough time to discuss your presentation. And then we move over to the next short talk, which will be given by Zoe Jardin. I hope I pronounced that correctly, from the Free University of Brussels. And she's going to talk about production assessment of hybrid directed energy deposition, manufactured fatigue sample with integrated effective structural health monitoring. So we're looking forward to what we are going to see from your project. Thanks.
Hi everyone, the pronunciation was perfect. I hope you can see my screen.
Yeah.
And hear me correctly. Okay.
Everything works fine now.
Perfectly. So yeah, I'm Zoe Jardin and I'm from the Vrije Universiteit in Brussels, and I'm currently doing a PhD there in collaboration with the Von Karman Institute for Fluid Dynamics that is located in Brussels as well. I will give a short overview here of the content of the presentation that is available online. And so the aim or the objective of this study is actually to assess the production of a fatigue sample of a rectangular shape, as you can see here, where we are trying to include circular cavities that we call capillaries, represented in red here, inside the sample. Now, these capillaries are used for a structural health monitoring technology that is called the ESIAM technology, that relies on the integration of these capillaries in additive manufactured parts in order to be able to monitor loads on that part, detect crack and localize cracks. It creates the propagation of pressure waves in these capillaries that can give us information about the health of the structure. Now, this production of this fatigue sample will be done with directed energy deposition that relies on the simultaneous laser and powder delivery. And it will be done with a hybrid in-house developed machine at the VUB that is called the MICLAT machine, that has one part that is used for additive operations for the printing process, and also that can switch very fast with subtractive operations such as milling and drilling, and it's a 5-axis CNC control machine. So for the printing of the samples, 360 ml stainless steel was used, and argon was used as shielding and carrier gas, and our melt pool size is around 1.66 millimeters. I give a short overview here. So 3 printing strategies were proposed. They all rely on a vertical build-up direction of the sample, as you can see here. And so the printing trajectories that are given as inputs to the machine were coded in MATLAB. And the first strategy relies on printing the first sequence of n layers of the sample, and then subsequently milling the contour and the top surface of these first n layers, drill a hole with a drilling operation through these n layers, and then continue following next sequences till reaching the final height of the sample. The 2 other printing strategies rely on the consideration of the capillary directly in the printing trajectory, and this will have different effects on the residual stresses and the cooling rates during the printing process, but also on the geometrical accuracy that can be reached. So these 3 are analyzed. Now, for the study, 30 samples were printed in order to obtain the highest geometrical accuracy, and the laser power was controlled on the contour of the sample and on the contour of the capillary with respect to the infill. And it was observed that the laser power, the mass flow rates, the layer thickness, and the overlap are closely related parameters and need to be tuned in order to get a good geometrical accuracy. And in this on this figure, you can see that these are full samples where we will drill after that, where the drilling operation will be done afterwards. Here, the capillary is directly considered in the printing trajectory. These are the results, just to give you an idea of such samples where this part was milled and this part was not milled yet. And you see the integration of the capillary that is around 3 millimeters through the different sequences that were printed, both here with the first proposed strategy and this one with the second strategy. And you can see here some in situ monitoring during the print process itself. So some images are taken coaxially through the nozzle here to see the quality of the melt pool. And these are taken from the nozzle head. And the aim of the study was also to evaluate with the SEM and optical microscope studies to evaluate the quality of the inner channel, because this is really important for the performance of this ESIAM system for the crack localization. So the presence of particles on the inner capillary can have a negative influence on the performance of the ESIAM system. So it was important to tune the parameters till reaching this finish. And as you can see, if you use the second strategy where you consider it in the print trajectory, you have a higher roughness due to these particles that stick on the capillary wall surface. And finally, to conclude, so for small diameters, strategy 1 is recommended. And then as a practical recommendation, we would omit the inclusion of the features down to 4 millimeters. And if you have a good laser power control, it can go up to 3 to 4 millimeter. It might be possible with a good laser control. And then for larger capillaries, the second and the third strategy are recommended. That was it for my presentation. If you have any questions.
Yeah, thanks a lot for your presentation. We have time for discussion here. I'm looking, no urgent things, but from my side, I mean, you want to monitor the fatigue properties of your final part in the long run. At the same time, you're bringing in some defect into the part with your capillary. So how are you going to deal with that? As on one hand, monitoring using the capillary, on the other hand, eventually weakening the part. So what's the strategy there?
Yeah, so indeed adding these open voids in the open cavities in the parts is reducing the structural integrity of the part. That's why we try to minimize these capillaries. And we have done some testing on samples, some fatigue testing that showed us which diameters we need to reach to not influence the fatigue of the component. And mainly it's triggered by surface defects on the inner surface of the capillary. So the goal was here to see how the roughness that we get out of this hybrid production process, if it's acceptable or not. And with the drilling operations, it showed that the fatigue is not affected for small diameters of the capillaries. This test campaign has been realized for as a first step with capillaries of 3 millimeters. And we saw that for capillaries of 1 millimeter and 2 millimeter, the fatigue performance wasn't affected. But indeed, we are lowering, we remove materials, so it's a bit a challenge to combine both.
And in terms, since you mentioned that the inner surface roughness is somehow relevant, did you also consider these electrochemical methods for cleaning out inner surfaces and also getting rid of this residual powder that might get stuck inside these capillaries?
Indeed, we have done some studies on that, on the post treatments that can be done on the capillary of the channel. Now, for the detection of a crack, it's not needed to apply this chemical etching because we can reach quite low roughnesses with the drilling operation. Now, if we want to go to the crack localization, it relies on the propagation of pressure waves in these channels. And there, the velocity, the propagation velocity is affected a lot by the obtained roughness. And there it's needed to post-process the part indeed with something like chemical etching.
Okay, yeah, thanks a lot. I'm looking into the chat also. No, nothing urgent coming along. Then thanks once more to Zoe Chardon for this very nice presentation. And we are moving towards the last presentation of this session, which is given by Josef Schlacher from the University of Leoben. I also see him here in the participant list. Yeah, we see you already, and we can also hear you. His talk is related to the mechanical response of 3D printed ceramics.
Yeah, thank you for the introduction. You're welcome to the short version of my presentation. The aim of the work was to determine the strength of 3D printed alumina in different printing directions and to study the influence of sintering condition and surface condition on the strength distribution. In the second work, we tried to use a design approach to significantly enhance the strength of 3D printed alumina ceramics. All the samples, alumina samples, were fabricated by using the lithography-based ceramic manufacturing technology, Alitos. So during my YouTube presentation, I addressed a few questions. So let's jump into this. So one sample set was sintered at lower temperature, and as you can see here, that the microstructure looks rather fine-grained with a mean grain size of 1 microns. However, there is a higher level of porosity directly at interfaces. When we take a look on the strength distributions, we can see that the characteristic strength in X and Y direction is very similar, statistically not different, but the Z configuration is significantly lower. If we take a look on the fractured surface, it is observable that some kind of delaminations in Z directions occur directly at the interfaces. So you can imagine if the applied stress is perpendicular to this delamination, this will compromise the strength. And on different locations, we can find such pores which are trapped between layers. By sample sintered at higher temperature, we can see a more homogeneous microstructure, which means that a lower amount of porosity is here, and so that there are no layers visible anymore. So most of the fracture origins were some small pores directly located at the surface. Therefore, there is no difference in the strength in the different printing directions, so they are very similar. And yeah, we can also notice a steeper lines, which means a higher viral modulus and a lower scatter due to the uniform fracture origins. So if we take a look on what is the influence of the surface condition, we can see that the tensile set, which shows some wavy structure, can compromise the strength, especially when the applied stress is perpendicular to the tails of those waves, and so they can act as stress concentrators or let's say as notches, and so the Z configuration or the strength of Z configuration is already lower again. So the last thing I would like to show you is we did a design approach to combine materials, so alumina with zirconia, toughened alumina, in a way that we if we combine ceramics which with strong interfaces, we can introduce compressive residual stresses. So depending on the chosen design with our volume ratio of 0.2, which means we need to think about the layer thicknesses. We can introduce compressive residual stresses after sintering, going down from sintering temperature when the thermal expansion coefficient of the middle layer, CTA, is higher than the alumina layer. So these compressive residual stresses can be used. So let's say this is some kind of a threshold strength, which means this has to be overcome to fracture the samples. So we need to overcome 320 megapascals. If we take a look on the strength distributions again, the calculation says that we reached a strength of almost of more than 1 GPa. And if we take in comparison to the monolithic samples, we can see that the difference is in agreement with the estimated residual stresses according to the calculations you saw before. I need to note that the samples were tested in biaxial loading, which means that this is used the ball-on-free ball test. On the fracture surfaces, we can see that fracture in the laminate structure always originates in the alumina outer region and not at the interfaces or at the middle layer. So thank you for your attention.
Yeah, thanks, Mr. Schlacher. That's, I would say, quite very impressive strength values, which you showed in your composite structures. So looking into the crowd, there's a question from Jan Torgersen.
Very impressive, I must say. What is actually the drawback of the higher sintering temperature? Is there accuracy loss? Why would you not use always the higher sintering temperature?
This study with lower and higher sintering temperature was especially used on purpose for this study. So actually the 1600 or 1650 sintering temperature is used.
Okay, but
maybe a comment from my side. As usually the problem with the higher sintering temperature is that you have grain growth, right?
Right.
Yeah, that's correct.
The grains become too large, and then this is.
We saw it also on the strength distribution that the higher sintering temperature it is a little bit lower with 400 megapascals, and the lower temperature in the good printing directions it is almost 500 megapascals.
Yeah.
Okay.
Oh, that's a general dilemma. Higher temperature would mean smaller voids because they close at higher temperatures, but at the same time, you also want small grain size, and this is rather achievable with low sintering temperatures. So you somehow have to find the perfect compromise here.
Okay.
A technical question. I mean, these laminar things and compress. That's an approach that's quite popular in glasses and glass ceramics, and so really something very appealing. Using such a technique, would it also be possible to somehow strengthen real 3D geometries, also not just a plain biaxial sample, but also a complex 3D geometry?
Yeah, in the future we can think about it. Maybe it's effect of processing, or let's say 3D printing. So it could be difficult but possible, and I guess the ethos is already working on complex multi-material structures, and yeah, should be possible.
It should be possible in the future. Yeah.
Yeah.
Good. Yeah. Okay. I think we have no further questions here. Chat is also empty. Then we are perfectly in time for this session. So thanks once more to all the speakers. Some very impressive presentations here and well presented by everyone. So thanks to our speakers, and also thanks for the discussion. And we are going to hear and see each other in the next session. So bye in the meantime.
Good afternoon. Can you hear me?
Yes.
Okay, thank you. Good afternoon. I'm Costanzo Bellini from University of Cassino in Southern Lazio, and I'm the chairman of this last session of this ESIAM conference. This session is about metamaterials and processability. I think we can start. We are on time. So the first presentation is a presentation from the NTNU in Norway. The presenter is Zuo Xu. I see him online. The title is Quasi-Static Behavior of 3D Printed Lattice Structure of Various Scales. So the stage is yours.
Okay. Thank you for the introduction. And first, please allow me to share my screen first. Yep. Okay. Okay, can everybody see my screen now?
From me, yes.
Yes. Yeah. Okay. So my name is Zhuo Xu, and I'm a PhD student from Norwegian University of Science and Technology. So today I will present the topic with quasi-static behavior of 3D printed lattice structures of various scales. So basically from the presentation before, so here I will briefly summarize the motivation and the outcome of this research. So basically for this project, we printed the lattice structures with PLA filament with the same process parameters. And the lattice structures we chose is the sheet-based gyro structures. And we classified these lattices into 3 categories, which is first is the scale effect at constant porosity. So which means all these lattices have the same relative density, but with different cubic size, unit cell size, and wall thickness. That's for the first category. For the second category, it's the wall thickness effect at constant cube size. So so basically all the lattices have the constant cubic size, but the wall thickness varies, and also for the unit cell and the porosity. And the last one is the unit cell size effect at constant wall thickness. So in this case, the wall thickness of all the sheet-based lattice is constant, but the unit cell size, cubic size, and the porosity varies. And then all these lattices went under the static compression at constant compression rate with 2 millimeters per minute. And then we calculate the stress strain curve based on the force displacement, and we can get some results. So for the lattices that under constant porosity, so with the lattices with larger scales experience higher ultimate compressive strength. And also under constant porosity, all the curves tend to reach the ultimate compression strength, and the densification point are nearly the same regardless of the wall thickness and scale. And also larger scale and the larger wall thickness will slightly increase the cumulative energy absorption per unit volume under constant porosity. And these are the results for the other 2 categories. So as we can see from these curves, most of the majority of the stress strain curve has a really smooth trend, but some of them have multiple peaks during the compression process, so which indicates the possible buckling of the structs under layer by layer failure mode. And also all the lattices for the accumulation of for the cumulative energy absorption per unit volume, since this is the unit relative density for all the lattice structures. So all the lattice show the linear trend for the cumulative energy absorption within the 0 to 50% of the string, which I think I think all the lattices have reached the densification point at 50% of the string. Yes, basically that's the conclusion of my presentation. Any questions?
Yes, any questions from the audience? Yes, there is a question from Harry Psioyos. Sorry for the pronunciation.
Can you hear me?
Yes.
Yes.
My connection isn't
if you want, you can
stable,
type,
so I hope you can hear me. What's the unit cell of your?
Sorry, I only heard unit cell.
Can you repeat your?
I will.
Sorry, can you
write it in the chat and you can freeze?
Perfect.
Yeah.
And in the meanwhile, other questions? Yes, I have two curiosities.
Sure.
Have you evaluated the mechanical efficiency of these lattice samples? So compared to the homogeneous solid structures, because the most advantage is the reduction of weight.
Sorry, can you repeat your question? No. Mechanical what? Sorry, I didn't hear that.
If you have evaluated the efficiency under the mechanical point of view of this kind of structure, efficiency in terms of strength to weight or stiffness to weight ratio,
strength
compared to a solid structure.
Oh no! At this point of view, yeah, we haven't done that. But I think this is a good question, because for this type of lattices, especially for the scale effect, so especially for the categories that we have the same porosities, but with different unit cell size and the cubic size. So for the in general, for the conventional manufacturing technique, there tends to be less defects as compared to the 3D printed, because for 3D printed, especially for the FDM printer, there is effect for the first layer, and also other factors like temperature distribution on the building plant and other parameters. So this will affect the internal defects of the structures. So when you have different scales, that will have you will have different results.
Okay.
Yeah.
And so you have also somewhat answered to the question of Harry. So the unit cell is the. So questions from Harry. Two questions. What's the unit cell of lattice structure?
What's the unit cell of lattice structure? Yes. If I remember, let me check with my original PowerPoint, because let me check with the specific number. So for the unit cell size, we started with the minimum is 4 by 4 by 4, so 4 millimeter by 4 millimeter by 4 millimeter, and then based on corresponding to the cubic size, because for the scale effect we need to have the same porosity, so then we increase to up to 16 by 16 by 16. So there are 4 different kind of unit cell size: 4, 8, 12, and 16.
I think the question was about the type of unit cell.
Oh, the type of unit cell. Sorry,
gyrodes, I think.
Yeah, gyroid and sheet-based lattice. Yes.
And what kind of defects did you identify in the lattice structure? Is the other question.
Okay, what, sorry, say it again.
What kind of defect did you identify in the lattice structure?
What kind of defect? Like, so far we are in the process of examining this under optical microscope. So as compared to other 3D printed structures from FDM. So for example, internal voids, this is one of the big issues for the 3D printed lattice, especially for the parts that has complex curves and geometries, because you can see the path from the nozzle. It doesn't 100%, even though we tried the best to optimize the process parameters, but still the infill rate is not really 100% yet. So yeah, internal defects or internal voids, yes, this is one of the major issues.
Okay, other questions from the audience? No, there are no questions. So thank you, Zoe, for your speech.
Welcome.
Okay, and we can start with the next presenter. She is Camille van der Rest from the Université Catholique of Leuven in Belgium. She is online. The title of the work is Enhancement of the Mechanical Behavior of LPBF HL alloys by Optimized Thermomechanical Post-Processing Routes. You can start.
Yes, good afternoon. Do you see my screen correctly?
Yes.
Okay, perfect. Thanks for the introduction. So this afternoon, I will talk to you about aluminum, silicon, and magnesium processed by laser powder bed fusion. And first of all, about the as-built material. It is well known, it has some significant amount of porosity after the process. It has also a specific mesostructure with some melt pools visible, and a typical microstructure with some silicon network being the white phase here, and also some silicon-rich precipitates, which are the white dots inside the aluminum matrix. And the idea of this work is to apply a specific post-treatment called friction stir processing to the material. And it consists in using a non-consumable tool. As you can see here, the picture. This tool will rotate and penetrate the material in order to have a thermomechanical processing of the material. The resulting microstructure is the following. So first of all, in terms of porosities, you can see that you have a significant decrease of the amount of porosities after this process. You have also a mesostructure that is more homogeneous. As you can see here, you have no more melt pool structures. But however, you have a growth of the microstructure and a complete globularization of the silicon network that was typical from the as-built material. In terms of mechanical properties, here you can see the static mechanical properties. And if you compare, so the FSP material is the green one, and the as-built is the blue one. And we also compare it with some stress relief material for the red curves. And you can see that the FSP material and the stress relief material have quite similar behavior from a static point of view, with a decrease of the strength and an increase of the ductility in comparison to the as-built material. And now if you look at the fatigue properties, so again, the FSP material is in green, the as-built in blue, and the stress relief in red. And in that case, you can see that the FSP greatly improved the fatigue life of the material, especially if you compare it to the as-built or even to the stress relief material. And if you look to, for example, fatigue crack growth propagation, Both FSP and stress relief material have quite similar behavior in terms of propagation of the crack. While if you look to the initiating defect, in fact, in the as-built and the stress relief material, we can quite commonly see a very large defect close to the surface as being identified as the initiating defect. While in the FSP material, we cannot identify clearly any initiating defect. So the delayed initiation is really the key explanation to justify this improvement of the fatigue life after FSP. And just to quickly show you two perspectives of the work of course, we can apply FSP on other LPBF materials. Here we have recent collaboration with Any Shape, a small company in Belgium on the scalmalloy. And you can see here that the FSP material also show very interesting fatigue properties in comparison to the heat-treated material. And secondly, you can also imagine as an application applying FSP on complex parts. And here I take an example we already saw Wednesday from Federico Uriati. And he showed that you have stress concentration here close to the fastening holes of these parts. And of course, you cannot apply FSP on the complex structure, but you can imagine applying FSP, for example, around these holes, where you can see that you have the failure. So again, thanks, Federico, for this nice example. And I'm open to your questions. Thank you.
Welcome. And questions from the audience? No questions. Well, I have just a couple of curiosities. You have considered in your work that the direction of the friction-free welding was perpendicular to the growth one in the presentation that I've seen on YouTube. And if you change this direction, for example, parallel to the growth direction, what can happen?
But for example, in the case of the scalmalloy, the direction of the FSP is similar to the building direction, so what you call the growing direction, and it doesn't change anything because after FSP, you have a complete homogeneous mesostructure, so you do not have any melt pool or things like that. So at the end, the properties after FSP are the same in both directions. So in the as-built material, if you make the mechanical test in the Z direction or in other direction, you can have different properties. But after FSP, the material is homogenized, so it doesn't change anything.
No problem at all. And another curiosity that you have partially answered in the last slide, as concern the complex shape part, this process cannot be applied on this kind of part. In fact, usually the additive manufacturing process, peculiarity of this kind of process is the possibility to manufacture very complex shape part. But in this case, you can apply the friction stir processing only on some parts. And what happens in the case of very thin part? You cannot apply it, I guess.
Of course, you cannot apply this kind of process, for example, on lattices or even of kind of organic shape, as you can see here on this part, of course. But concerning very thin part, you can change the tool also. For example, here we have a tool with a pin, so it's the small part of the tool that is penetrating the material that is 5 millimeter. But you can imagine having also very smaller tool. But of course, you will never be able to process very, very thin sheets. But I think around 1 millimeter, it should be okay. And in the case of some, sorry?
For the forces?
Yeah, of course, the parameters will be adapted if you change the tool and if you have complex geometries. But FSP can be applied with robots. It's already used as a welding process with robots. So you can follow already 3D path with this kind of robots. So you can imagine using this kind of robots to apply the process. For example, in this case, around on that surface, maybe on both sides of that surface, and also around each hose, for example, in order to reinforce this parts of the component.
Yes. And there is a question from Harry.
Excuse me, but I haven't, at least this is not clear to me, how you can process a complex part with the friction stir welding, with the friction stir process.
So for example, if I take this example of this part, I never try to process this part. It's an example from the conference here. I found it interesting on Wednesday, but I think you just need to clamp the part, and then you can use a robot to go for FSP around these holes. So just, oh yeah, okay. I don't know if you see my my mouse, but you can using FSP just around these holes. You do not have these bars, of course, but on the part itself, you can using FSP and come with the tool here around these holes in order to reinforce this zone only. Of course, you cannot apply it on the body of the component, if I can say that.
So this post-process is restricted to the complex geometries that are allowed to be processed, that the machine tool can beam them.
Yes, yes.
Can treat them.
Yes, yes, of course. But usually, even the parts with complex shape will need some machining after in order to create the holes or to drill something. Or I think it's for some, maybe not all the parts, but it often occurs that you will need to machine somehow the part or even a small zone of the part anyhow. So I think it's not applicable for all the parts, of course. But for example, for this part, it could be interesting for this component.
So this process is topically related, is regarding the object.
Yes, it will be depending on the object and the application. And if you have a part that where you need to drill holes after the additive manufacturing process, then you can, for example, apply this process this post process in addition in order to reinforce one zone of the component.
Okay, thank you.
Okay. Thank you. Thank you for the presentation.
Thank you.
Other questions? Okay. Thank you. You're welcome. So the next presentation, presenter is Erfan Maleki.
Hi everyone.
Good afternoon. From Politecnico di Milano. And the title of the presentation is Effects of Hybrid Post-Treatments on Fatigue Behavior of Notched LPBF, Aluminum Silicium 10 Magnesium, Experimental and Deep Learning Approaches. So you can start with your presentation.
Hi everyone, can you see my screen?
Yes, if you... Okay, thank you.
Okay. Hi everyone, I'm Erfan Maleki. And I want to present our study on the effects of hybrid post-treatments on a fatigue behavior of notched LPBF, aluminum silicon to magnesium, with two different approaches of experimental and deep learning. This work is part of my recent PhD studies in Politecnico di Milano Mechanical Engineering Department. And I'm the third year PhD student, and this work is performed under supervision of Professor Marco Aliano and Professor Sara Bagaiba. As I don't have lots of time, actually, in the first parts, I will explain them briefly, the introduction, the example procedure, and then I will go deeply to the neural networks development and results and conclusions. it is well known that additive manufactured materials mostly have poor surface quality and irregular features on their surfaces, which can be characterized by partially melted and unmelted powders and also spatters. Here you can see examples of two different technologies that we use for different fabrications: selective laser melting and electrobeam melting. In both of them, we can see lots of defects in the surfaces. And as you know, most of mechanical failures, especially the fatigue behavior, is very sensitive to the surface properties. And if we have lots of surface defect, then we're gonna get low fatigue performance for the material. That's why lots of efforts have been done on the surface post-treatment of additive manufactured materials, especially on the metallic parts. Based on our review paper about the applied surface post-treatments on the AM metallic materials, there are 4 main categories for surface post-treatments. First one is with material removal, with material removal. The second one is no material removal, and the third one is coatings. And combination of these 3 treatments gonna be in hybrid treatment categories, in hybrid treatments. It was found that shot peening can be very effective on fatigue behavior improvements of the additive manufactured materials by inducing compressive visual stresses, surface morphology modification, and also grain refinement in the surface layer, which can increase the hardness and apply surface hardening. Also, it was found that chemical treatments can highly reduce the surface roughness, and they can modify the surface morphology in a fine way. Also about the hybrid treatment, it was found that different treatments such as heat treatment or hot isostatic pressing (HIP) combined with other surface treatments can be used on the materials to gain desired surface or bulk properties. For example, here in the work, a combination of heat treatment and sandblasting, a combination of heat treatment and shot peening is worked, and in some other works, combination of etching and also PEO. Also, for example, combination of machining and polishing are already applied in the literature. In this study, we investigated the effects of shot peening, heat treatment, and electrochemical polishing individually and also combined together to investigate the fatigue behavior of the notched fatigue samples. Here you can see the parameters of the LPBF process and also shape and dimensions of the notched fatigue specimen. In design of the notched fatigue specimens, the notch root radius of 1 is considered to be ensured that we can reach to the notch root by impacting the shot media. Then we considered T6 heat treatment on the material for homogenizing the microstructure. Then we used shot peening with steel shots with aluminum intensity of 10A and full surface coverage of 100%. And also we applied electrochemical polishing, ECP, using
Sorry to stop you, Erfan. I'm
okay.
sorry. You should go to the conclusion because the time is
okay.
Almost
so
ended.
Combination of all of these treatments, we got let's say 8 different series of specimens. Then we use artificial intelligence to model the process. We considered parameters of yield strength, elongation density, surface roughness, surface hardness, surface resistance, and surface modification factor as inputs, and also we considered fatigue line as the output of the process. We use parameter of the correlation coefficient R2 for performance evaluation. Details discussion and questions about this development is presented also in the uploaded video. You can see there. The main novelty of this study is explanation of the new parameter in additive manufacturing as a surface modulation factor. You can see here in the as-built or heated material, we have lots of surface notch root. By applying shock cleaning, it's going to be better. But after applying electrochemical polishing, it becomes better and better, and we have the best surface quality in the electrochemically polished. Then we assign different values, numerical values, to each of these three conditions. And then we develop neural network using these data. And it was found that by increasing the number of neurons in each layer, we can get higher accuracy. Also, it was found that although we had small data set of 24, we can reach to the 97% of accuracy by using pre-training using a stack autoencoder, which shows that we get to the very high accuracy. After applying the neural network modeling and obtaining best neural network architecture, we generate the model function with the best condition. You can see the best architecture of network here. Then we applied a sensitivity analysis on the inputs to obtain the highest importance of each parameters on the fatigue life. It was found that surface modulation factor has the highest importance, and then elongation as a parameter of the material. Then we applied parametric analysis using model function to estimate the fatigue life using these two terms, surface modulation factor and elongation. It can be observed that by increasing surface modulation factor and elongation, which can be increased by the heat treatment, we can get higher fatigue life. And thank you so much for your attention. I'm ready.
Okay, thank you, Erfan. And are there questions from people at home? No, I have a question.
Yes, please.
Have you studied or analyzed the fracture surface of your specimen? And
yes.
If yes, what are the results, the highlights?
Yeah, actually, we deeply analyzed the fracture surfaces in all of treated specimens. It was found that in the, let's say, in the as-built samples and also treated samples on the as-built state, we have some major crack initiation sites, one or two, but in the heat-treated samples, we have multiple crack initiation points from different areas of the notch root. Also, it was found that the fracture site, if I can show you here, the fracture site in the as-built material is above the notch root on the upper skin surface. By applying heat treatment and other treatments, it moves down to the notch root direction, and we can, by applying, it was found that by applying these surface post treatments and other treatments, we can eliminate the sensitivity of the body behavior of notch samples on the surface roughness.
Okay, no questions from other people. So, thank you so much.
Thank you so much. Thanks.
Welcome. And then we can jump to the next work of Julie Geisen from the University Catholique de Leuven. The title is Efficient Optimization Methodology for Laser Power Bed Fusion Parameters to Manufacture Dense Part Validated on Aluminum Silicium Alloy.
Hello.
Hello.
Can you see my screen?
Yes. Perfect. Now it is bigger.
Okay. So I will make a short summary of my presentation.
Yes,
which is about a methodology to optimize the LPBF parameters in order to manufacture dense and with optimal mechanical properties. So how did we do that? So first we have started with a design of experiments in order to have something which is efficient and not too much expensive. And we have chosen to use a central composite design because it's the type of design of experiment that we use when the goal is to optimize. Then the methodology is divided in 3 parts. So first we have manufactured single scan tracks, because if we suppose that a part is made of the overlapping of single scan tracks, therefore the properties of the part will depend on the properties of each single track. So for that, we have analyzed if the track is continuous to avoid to have porosity. We have checked that there is enough penetration to have good cohesion between the new layer and the previous one. Also, we look at the height in order to build efficiently the height of the part, and at the contact angle, which should be close to 90 degrees in order to have a good accuracy of the manufacturing. So that's the first part. So we analyze the geometrical feature of the single scan tracks using ESIAM. Then we have manufactured cubes with different set of parameters, and we have analyzed their densities by Archimedes method. And the last step consists in analyzing the mechanical properties of 12 tensile specimens. Then we took the results of all these 3 steps, and it enabled us to build a statistical model, which will be able to predict all these results, so the density and the mechanical properties, in function of the LPBF parameters. And so we can see here that in green, we have the optimized parameters. With these optimized parameters, we could compare the experimental mechanical properties and density with the predict one of the model, and it was really in good agreement. And we also have seen that these mechanical properties were better than the one reported in the literature. So it's a really interesting methodology to optimize the parameters. We have only used it for the moment on aluminum silicon 12 alloys, but it gave really good results, and we hope we could test it on other materials. So if you have any questions.
Questions from the people at home or in the office? Yes, Harry?
Once again, I take my turn in questions. To be clear to me, this is a density optimized method, right?
So we optimized the density and the mechanical properties. So we focus more on the mechanical properties, but we know that the density, if we have something really porous, it will also give bad mechanical properties. So we have also analyzed the density.
But mechanical properties are not, but mechanical properties are function of density, right? Or you just curious about the grain size or something like that?
So the mechanical properties so the density will have influence on the mechanical properties, mainly on ductility, but the LPBF parameters will also influence the melt pool geometries and the microstructure, so the size of the cells, and all these will also have influence on the mechanical properties. So we directly make the link between the LPBF parameters and the mechanical properties without really seeing if it's more microstructure of density which have influence, but both have influence.
Other questions? I have just a curiosity, and I think that another target very important for industrial application is the manufacturing cost, so the minimization of the costs. And if we include these the costs among the targets, how your conclusion can change if you have an idea?
So here we think we minimize the manufacturing cost, because to manufacture just one single track, it's really not a lot of material. And then you have to manufacture 18 cubes and 12 tensile specimens, but you can have really strong conclusion after that. And you're sure of the influence on the mechanical properties, etc. So with the design of experiments, we could really minimize the number of trials that we have to do to have this conclusion. So if we minimize more this number of trials, we could not get conclusion which would be that strong.
Yes, but I mean, in generally speaking, I think that if we add the cost, the manufacturing cost, maybe the optimal region of parameter will be reduced. I think maybe that some, for example, too low speed are not so cheap.
Yeah. Yeah, like you can, for example, say, okay, I want a scanning speed which is more than this. It should be also possible to add the manufacturing cost with this, but then you have to also increase the laser power. So here we were limited with the laser power of our machine. So, but yes, it's possible to optimize this also and to add this in the model.
Mm-hmm. Thank you.
Thank you.
Welcome. And so we can jump to the last presentation of this last session. Presentation from the Université Catholique de Leuven. The presenter is Nicolas Nothomb.
Yes.
And,
hello.
Yes.
Can you see my slide?
Yes, you can enlarge your
okay, perfect.
Screen. The title is Hot Cracking Suppression by Power Modification of an AL7075 alloy produced by laser power bed fusion, and first insights in the improvement of its fatigue life. Very long title.
Yeah, a bit long title. Yeah.
Yes.
So thanks a lot for the thanks a lot for the introduction. And so as you said, I'm Nicolas Nothomb, and I'm just finishing my first year of PhD thesis in UC Louvain in Belgium, and I will talk about hot cracking in the 7075 alloys. So I have compared 4 different powder during my presentation. I have compared the classical aluminum 7075 without any addition, which is an alloy which is highly susceptible to hot cracking during the process. And I have compared it with 2 different powder mix. So aluminum 7075 with zirconium hydrates that were added by mechanical mixing, and the difference between the second and the third powder is the amount of zirconium that is added. So one with a low amount and one other with a higher amount. And finally, I will also compare the first 3 powder with coated powder, in which the zirconium hydrate is added thanks to a plasma process patented by AM4AM, which is a startup in Luxembourg. And so it will use a plasma process to really draft ceramic powder on the surface of the aluminum 7075 powder. So I have analyzed a few things, but so concerning the powder, I have compared the plasma coated powder with the mechanical mixed powder, and I have shown that there is a really less big zirconium hydrates aggregates that are really detrimental for the mechanical properties in the coated powder. Afterwards, I have also analyzed small zirconium particles that are grafted on the powder, which are the particles that we wanted, because they will form some sub-micrometers aluminum-3 zirconium precipitates at the beginning of solidification that will generate a grain refinement and so suppress hot cracking. So once again, the coated powder was better because there was more particles on them. And if we go to a small summary table, so like I've said, the coated powder is better regarding the zirconium distribution. Then concerning hot cracking, when the powder mixed with a high content of zirconium shows no hot cracking whatsoever. The coated powder shows no hot cracking for the optimized parameters, but the two other powder shows hot cracking, which want to be avoided. And it is mainly due because the coated powder and the high content zirconium powder have really small grains, which avoided the hot cracking. And I have also analyzed the effect of a classical T6 heat treatment on these four powders. So T6 treatment for the 7075 is 1 hour at 480 degrees of solution heat treatment, followed by 24 hours at 120 degrees. And what I have observed regarding the microstructure and the micro harness is that the difference between the complete T6 heat treatment and only the solution heat treatment is really low. There is not much difference in the microstructure, and the hardness is roughly the same for the different alloys. So it means that there is still a lot of room for improvement for the heat treatment for the specific LPBF alloy. And so we are currently optimizing this heat treatment to obtain better mechanical properties. And currently we have obtained 121 hardness Vickers for the hardness. So it's quite good. And we can see that also the coated powder has a lower hardness than the mechanically mixed one, probably because there are a lower amount of smaller grain in the microstructure, like I've explained during my presentation. And so I'm just gonna stop there for my presentation now, and to leave time for question if there is any.
Thank you, Nicolas. Are there questions? From people? I have some questions. First of all, I have seen in your presentation that by adding an higher quantity of zirconium or applying the coating process is more or less the same for the hardness. And about the costs, are there differences? Which treatment is better under the point of view of the costs?
So of course, coating a powder with the plasma treatment will cost more than just mechanical mixing, but currently it is still under this technique that is still under development. So there is no final cost at this time for the plasma treatment, and we still must analyze all the difference, not just the micro hardness, but do some tensile test and also some fatigue later on, to see that if it is really a bad thing to do the plasma coating, because the powder is really of better quality. So we expect it to have better mechanical properties due to the lower amount of zirconium aggregates. So before doing let's say the economical analysis between the two different methods, we must first analyze completely the methods, because we hope and we are confident that it will be better with the plasma coated powder.
And another question. You said that you are working on also on the aging treatment.
Yeah.
And you are improving this treatment. And which are the which modifications are you considering? So on the temperature, on the length?
Currently, we are considering mainly, first of all, the temperature of the solution in treatment, because yeah, the 470 is the classical one, but we will see if there is other temperature that can work, and to really understand what are the influence of it, because clearly the classical T6 it's not optimized, because the aging treatment is nearly has nearly no effect, so it's not a good age treatment. So firstly, the temperature, and we will see if we can just suppress the aging treatment for other solution treatment temperature, and we will see which one will be the best for our samples.
Okay, thank you for your kind answer.
Thank you.
Other questions from other people? Either on the chat. Okay, thank you, Nicholas. And this was the last scheduled presentation, and we are also in time. So we have now a 10 minutes break, and then there is the closing ceremony. So see you in 10 minutes, and goodbye from me.
Hello, everyone. Can you hear me?
Yes, yes.
Yes.
Okay.
Yep.
Thank you.
Yes, we do.
Very good. So thank you very much for attending ESIAM 21. It has been a pleasure and a real honor to host, also if it's only virtual, you all at this event. So it's always difficult to say something after a conference because so many things have been said. So I will just start with the positioning of our conference, and I think we are quite in a unique spot with the scope of the conferences because when we look out there, what kind of additive manufacturing conferences are around, we see a lot of terms, a lot of interesting applications and a lot of interesting scopes. Materials is definitely one that we also tackle here. But what can be said is that definitely these words of integrity, mechanical properties, fracture and fatigue, not that they are not there, but this is not probably the scope of other conferences. So we are quite happy and quite intrigued that there's so much interest in these topics around additive manufacturing, and it doesn't come from anywhere. If you look at the revenue, probably all of you have seen this, but the revenue from final part production within the field of additive manufacturing still low, but rapidly rising. I think one of the biggest rises in revenue within the field of additive manufacturing. So this is definitely a place to be. We also see this from the submissions to the conference. Definitely the fatigue of AM metals is kind of exceeding the charts, so to say. We have over 25 submissions in this field, and you can see that where AM metal fatigue and fracture and also polymers is important, like in aerospace and lightweight, and already applied. There we also have a lot of submissions. The characterization with this also becomes important, and we have also quite some submissions on fracture of AM polymers and metals. So we are really intrigued by the large interest that we have. And what we can say and what we want to state is that we want to put the failure perspective to the field of additive manufacturing. So everything starts with a big failure. Failure is the only thing where we really learn something. And we can, as mechanical engineers or as people working in the structural integrity, we can deal with failure. We also failed to organize this event in Vienna, which was unpredictable, but probably more unpredictable than the failure of our mechanical components. But I want to acknowledge especially the E308, where I had the honor to be part at some time ago during my PhD, and especially the group of Jürgen Stampfel, who was actively involved in setting our event up in Vienna, which did not happen, but that does not diminish the work that they have done. So thank you very much for that. I hope that we have an occasion in the future to repeat this, or not repeat, but do this in Vienna. I think also the attendees did not like it very much that we cannot come to the beautiful city of Vienna. At least I did. I want to, sorry.
And we are certainly very willing to further contribute to ESIAM. Also, just as a short remark from my side, as it was a great virtual event, and I think if ESIS let us do, we are certainly very willing to further contribute to these activities.
It is great to hear. So definitely we didn't want to cast you out by this decision. Yeah, special thanks to our plenary speakers. I think we really enjoyed both the industrial aspects and also the fundamental scientific aspects, starting with a very deep scientific talk by Guyan Kian, and also Matteo with Armin presenting a little bit the perspective of the end user applications in industry. Eric also more on the broad overview of what is possible within additive manufacturing, and also Anton with his nice gyroid and lattice structures, and Klaus with an overview of the software capabilities and how this can be converted or converged with process simulation. So thank you very much. I think you really opened the stage to a very fruitful discussion on the later speeches and talks, and this was really great. Thank you. A special thanks to also the conference chairs. Our setup was a little bit different than it is known from other conferences. So that put an additional demand on the conference chairs. So it was a trial, and I think it was very successful. But of course, it depended very much on you, on your knowledge and your enthusiasm and your guidance through this session. So thank you very much to all of you who have participated. I want to thank also people behind the scenes that we did not see at the conference. That is Julia Anna Schönherr, also part of the group of Jürgen Stampfle at TU Vienna, who was initially very involved in setting up the homepage and all the kind of tools that are required for holding these conferences. And then also Vittoria Di Cocco, who is responsible for the treasury at ESIS. So thank you very much. I want to also look a little bit into the participants. We can see that everyone, or it was expected that the event to take place in Austria. We see a high density, very low porosity at the center of Europe, which gives us an indication that everyone expected to go to Vienna. So thank you. We have quite a lot of participants despite being an online event. So we are very happy about this, but we also span over the whole world, which shows also the kind of importance globally of this aspect. I want to also announce the Best Speech Award, and we have not one, but we have several. We could not decide between Sandra and Florian for the Best Speech Award in terms of student and contribution to a session, because you both really were very active in the discussion of this fracture of EM polymers. So we want to give you both an award together, and then we want to also give, in terms of senior speaker, we want to give an award to Gianni Nicoletto, and maybe Filippo can say a few words.
Yes, I think that award to Professor Nicoletto is given for his contribution to the discussion, and also for the level of his presentation. Is also a contribution because for me, is an example. I don't want to say that he's old, but he's investing still a lot of time in research, and that is an example for me, and also for the younger generation, as to and this is very important message for us, for the young people. So I think that award is very well deserved. And I'm very happy that he is receiving this prestigious, I don't know if it is prestigious, but this recognition from us for his contribution and for his continuous work in the additive manufacturing field, that is well acknowledged from the scientific community around the world, as we have seen in this conference. I don't want to spend much more. I think that is.
May I thank you? May I thank you?
Yes, of course. You are welcome.
So not only you, of course, but also the other colleagues from the ESIAM community. Of course, I'm, let's say, honored. As you said, I'm rather old, but still enthusiastic about working with younger people in research. And I would say metal additive manufacturing is really challenging but enthusiastic, well, very, let's say, appealing topic with a lot of new things that need to be still discovered and understood. And especially we need to push the applicability in industry of this technology. That will be really the success for the technology. But I think we have here a very nice community, very active community, a lot of younger colleagues, very active and also deserving a lot of future successes in the organization and in the achievement of scientific results for the future. So thank you to all of you for thinking of an award to me. Thank you.
Thank you so much.
Our pleasure. And then last but not least, we want to announce an award for Maria Jose Marquez. Excuse me if the pronunciation is not correct, for the best online conference in terms of slide design and in terms of also the motivational aspects. It was a very thorough talk. Thank you for that. For all of you that received this award or that get this, basically we will be in touch. You'll receive a gift, so it's not only this icon on the side, but you will receive something which we don't tell yet, but we will be in touch. I want to also thank the organizing committee. There's a lot of work behind this one. Luca and Brecht have been there since the beginning of ESIAM, so they have been kind of also the founders together with Filippo and me. And now also Jürgen and Francesco, they were really active and provided a lot of support. I want to also acknowledge ESIS, the European Structural Integrity Society, in this regard, because we are all acting under the framework of ESIS. So thank you very much. And with that, I actually already exceeded my time. I don't want to stress you further. It has been 3 days of online meetings. So thank you very much. And we will be in touch for the future ESIAM in 2 years. We yet don't know what will happen, but we will keep you posted, and I hope you will join also next time, hopefully physically. Thank you very much.
Thank you for this nice conference. Very well organized. Thank you.
Thank you very much.
Thank you. Goodbye.
Thanks a lot. Bye-bye.
Thank you. Congratulations.
Bye-bye.
Thank you. Bye.
Thank you. Goodbye, everyone.
Bye.
Thank you. Bye.
Thank you. Bye.
Thank you and goodbye.
Good weekend, everybody. Bye.